if you have decision tree, and this is assuming the error, okay, and this is the depth of the tree. What happens in case of training, right?
The error will gradually reduce.
The error will gradually reduce, right? So as you keep going deeper and deeper in the tree, your training error keeps reducing, right? But what happens for the test error?
It may increase.
It may, and most likely it does, right? So what happens here is it goes something like this, and you have this high gap between the training error and the test error. You see this? You see this thing? You see this thing? So this is what we might say the test error or the generalization error in that sense, and this is for the training, right? Good. Now, what happens in general once we speak about Ensemble and also in, specifically in case of Adaboost? So we have here, let's assume that we have the number of weak learners. And we know that weak learners could be any classifier. It could be decision stumps, it could be decision trees, it could be logistic regression, and other classifiers, right? So what happens here is that in validation, so of course you keep increasing, you keep decreasing the, I'm sorry, the train error. You keep decreasing the train error, but what happens in the validation error is it's more robust for the tester, I'm sorry. So this gap in case of Ensemble learning or Adaboost is narrow. This gap is narrow, right? So what happens is if you keep adding more and more ensembles, the weak learners, you don't get this a lot of overfitting. So generally speaking, we can say that ensembles are robust to overfitting. Now we have to keep in mind that robust overfitting generally means it holds, but again, what happens if you keep increasing more and more learners, weak learners? So you go from hundreds to thousands and thousands to 10,000s or tens of thousands. Of course, then you might see this trend on the test set. It goes down and then it starts increasing a bit. So there will be some overfitting there, but not as much as, for example, a decision tree or the commonly speaking, a complex single classifier. So there might be eventually some overfitting, but this table area is a very long area. So for example, starting from few hundreds to few thousands or even 10,000s, this will be a stable area. And there will be very small increase in the error if you keep increasing more and more. So yeah, there is some overfitting, but generally speaking, is quite robust to overfitting. This is one of the area in machine learning where it's a lot of discussions why ensemble learning is more robust to overfitting, and there are many different explanations. You can also look at this topic online and see in the recent research, there are many different explanations for that, right? One explanation says that what happens is, for example, think about this, that you have these samples. These are positive samples, let's assume, okay? And these are some negative samples, assuming. And this is one negative sample which is here, let's assume, okay? What happens in traditional classifier is, if you are going to come up with a complex decision boundary, right? High order polynomials or whatever, you will have a region of decision boundary which accommodates this particular sample, right? You see my point? Okay. Somehow OneNote has stopped working. I hope it comes back again. If I'm not wrong, can you see the screen now or no?
Yes.
Yes.
It's there. The screen is there.
Yeah.
Yes.
Okay, very good. So, okay, it got restarted. So again, let me come up with some sort of decision boundary. So assuming that you have a single classifier, which is a complicated classifier, high order polynomials or whatever, you will have some complex decision boundary, and assuming that classifier is going to accommodate for this by some sort of decision boundary, right? And it could be different forms. This is just an example. Okay. So let's assuming this is a classifier. What happens now is, because you have this region, right, which is allocated for negative class, any positive samples on the test is misclassified, right? You see my point?
Yes.
Anything which comes under that region, because the way you trained, that region was allocated for the negative class. But now those test samples, because you're assuming this common pattern of positive samples being here, again, I'm not sure what's happening every time it's restarting. So somehow in machine learning, the OneNote is not that happy. Okay. Okay. So here we have, so this is what we are expecting, right? We are expecting in the test case, all those samples are positive, most likely to be here, but these samples are going to be misclassified. Are you with me now?
Yes.
Now, what happens, the one explanation of why Ensemble is normally quite robust to overfitting is this idea that in case of Ensemble, what happens is, assuming again, you have these positive samples and some negative samples, okay? And there's a negative sample here, and assuming these are some positive samples again. So what happens is, just focus on this outlier, so to say. What happens is the decision boundary for the ensemble, because it's a collection of multiple classifiers, this is a very tight decision boundary, actually, a very tight decision boundary. Now it's so tight that hardly only this sample belongs to this region. It's very difficult to fit in other samples. So what will happen is, if you do the actual test, you have those same samples which are around this still belonging to the positive class. It's very difficult to find another positive class which is still in that small tight region. Is this making sense?
Yeah.
So this is something what is a very good explanation of why, generally speaking, ensembles and Adaboost are robust to overfitting, generally speaking. So this is something to keep in mind, right? So again, to conclude our discussion on Adaboost, it's a very powerful classifier in ensemble learning. And it's generally speaking, ensemble learning is a very promising area of machine learning. And we need to make progress in individual classifiers. But at the same time, if you're speaking about making a machine learning project, at the end, generally speaking, it always helps to have some sort of ensemble at the end. So you might have some good classification and ensemble at the end. And if you see many of the competitions in Kaggle, there are two types of winning systems. If you're speaking about some deep learning system where you have huge amount of data or raw data, mostly the deep learning systems are the winners. But you're speaking about structured data, all those traditional rows and columns of features. Generally, any form of ensemble learning, mostly random forest, gradient trees, stuff like that, right? They are Adaboost. So ensemble learning is generally a winner, right? So it's very important to keep in mind ensemble learning in your repertoire of machine learning techniques. So if there's no more question, yes, please.
Can ensembling be applied to regression problems?
Oh yeah, ensemble learning can also be applied for regression problems. So what you can do is, again, for example, think about this, for example, regression in case of bagging. What will you do is you'll fit different regression lines, right? So each bootstrap aggregating this training sample batch, in case of bagging, you're going to fit a regression, right? And what will you do in the case of testing? You will use all those regression, and everyone will give you a value, a y. And your final regression is basically you can take a mean of all of that. So yeah, it does apply. Ensemble learning can be applied both for regression as well as for classification. So generally what you do in classification, you have some sort of majority voting or weighted majority voting. In case of regression, you can have some sort of mean or weighted mean. I hope you follow this idea.
Yeah, clear.
Yes, yeah, it's clear.
Good. Yes, please. So anything else before we move to our next ensemble, which is random forest?